Good afternoon, class. Tonight we're going to learn about acceleration. Now, last night you read a little bit about acceleration, and you know that acceleration is the rate of change of velocity. So in order to calculate acceleration, we need to know how much the velocity changes, and then we need to divide that by time. That's what rate means, something divided by time. So our final velocity minus our initial velocity divided by our time would give us our acceleration, and the units would be meters per second in the numerator divided by seconds. That's why we get a unit meters per second squared. Recall from our motion sensor lab and our motion graph interpretation worksheets that if an object's accelerating from rest, we see that it covers more and more distance each second. This is if an object is speeding up. And so the position versus time graph is going to show an increasingly positive slope. And since the slope of a position versus time graph is velocity, we're going to show that on the velocity versus time graph. We're going to see a line with a positive slope. We're going to show that the velocity is increasing the same amount each second. So this is just a line, and we know the equation of a line is y equals mx plus b. So this formula, which Galileo discovered in the 1600s actually, is just the equation of a line, where m, the slope of this line, is change in velocity over time, because slope is rise over run, so that's acceleration, where the x is time, so this is mx plus b. The y-intercept is the initial velocity. Now, if the initial velocity is 0, this line would just start down here at 0 and do the same. Now, for position versus time graph, we see this sort of parabola shape, the parabolic shape that we talked about today. And that's why the square is in here. It's covering more and more distance each second. So we have to show that with a square. And so what we want to do is learn how to solve problems involving acceleration, velocity, time, and displacement or distance. I'm always asking you to show your work, and so this is a specific way I want you to show your work. First thing you do when you read a problem is to identify what you know and what you don't know. So identify the variables you know. You might know the initial velocity, the final velocity, and the time. Then you're going to choose a formula that relates what you know to what you don't know. Then you're going to substitute those values into the formula, the actual numbers, and then you're going to solve for your final answer using the rules of algebra. Include a unit and the correct number of significant digits in your final answer. Then you're not really done. Think about your answer. Does it make sense? So let's go through some examples. A bald eagle begins a descent at 5.0 meters per second to catch a smaller bird for dinner. 8.0 seconds later, with a speed of 9.0 meters per second, the eagle caught its prey. What was the eagle's acceleration? So what do we know here? We know the initial velocity, we know the final velocity, and we know the time. Those are our known variables. Our unknown variable is, what is the acceleration? So what we're going to do is we're going to choose a formula that relates what we know and what we don't know. A equals delta V over T. So our change in velocity is 9 meters per second, our final velocity, minus 5 meters per second. So what is our change in velocity? That's right, it's 4.0 meters per second. And our time was 8 seconds. And if we solve for our acceleration, we get, that's right, half a meter per second each second. Remember, it's acceleration, it's meters per second squared. What that means is the bird accelerated half a meter per second each second. Okay, let's look at a different example. A motorcycle accelerates 4.0 meters per second squared east from a stoplight for 5.5 seconds. What is the motorcycle's final velocity? So what do we know? We know this is the acceleration, meters per second squared. This is the time, 5.5 seconds. We want to know the final velocity. So we also know one other thing. We're accelerating from rest. So our initial velocity is 0. So here's our formula we're going to choose. We're going to plug in our acceleration, 4.0 meters per second squared, times 5.5 seconds. What is our final velocity? That's right, it's 22 meters per second. Does that make sense? And yes, it does. Each second we're gaining 4 meters per second of velocity. So if we do that for 5.5 seconds, we're going to gain a little over 20 meters per second of velocity. That makes sense. And finally, how far did the motorcycle travel during this time? And that's what we learned on the very final page today of our worksheet. So let's go ahead and see if we can figure this out. How far would be the formula with the square in it? Delta x equals the initial velocity times time plus 1/2 at squared. Now remember, our initial velocity is 0. So this first term cancels out. And we just need to take half of the acceleration, which was 4.0 meters per second each second, times time, which was 5.5 seconds. And we need to square that. So remember order of operations. We have to square the time first. So what is 5.5 squared? I'll let you plug that in your calculator. That's right. It's 30.25. And we have to also apply that square to the unit as well. So we have 30.25 seconds squared. Don't go and square the number again. You've already squared the time and you squared the unit. And we need to now multiply that by 4.0 meters per second squared and 1/2. And what do you get? That's right, you get 61. And the unit for distance you already know is meters, but let's go ahead and look here. We have meters per second squared, that's divided by second squared, times second squareds. These second squareds cancel out and we're left with just a meter. So that is how you would solve for the displacement or the distance traveled for an accelerating object. And we'll learn more about this in class tomorrow. See you then.